welcome once again in class of design of steel structure. We are learning the tension members. So in last lecture we have seen some problems of the uh, design and as well as the load carrying capacity of the tension member. So today we will continue with the another problem, that is for the uh, eff- effective net area or net effective area of the plates. So I am Mr. S. Sogule, Assistant Professor, Civil Engineering Department. This is the next problem, that is a 300 ISF, that is Indian Standard Flat 8 is used, which is ISF is used for the flat plates. So is used as a tension member in the lattice girder. It is connected to a 12 gusset plate by 18 5 hand driven rivets. Calculate the maximum force member can carry if the chain riveting is done and the zigzag riveting is done. So phi is given, that is 18 So the gross diameter is 18 plus 1.5, that is 19.5 So here you can see this is the chain riveting and this is the zigzag riveting has been done. So as we know, these are the sections, that is 1 1 2 2 and 3 3 in the chain riveting where the failure can occur. And in case of this zigzag riveting, there are so many particularly failure planes. That is, first you can see this is 1 2 3 4 from this plane, or by this failure can occur. This is, I will draw the line over here or make it dark. This is 1 2, this 3 hole, and this is the fourth part. So this is 1. Then the failure can occur in this way: 1 2 5 8 9 and 10. So this is one way. The third way is 1 2 5 3 and 4. So this is another way. And the last way is, or the another way is 1 2 5 6 7. So these are the different sections through which the failure can occur. Let me erase this. So these are the different way by which the failure can occur. So we are going to see the different scenarios and what will be the strength, or according to this how much the force member can carry. So first, if chain riveting is done, the critical section can be this 1 1. Critical section can be this 1 1. So here you can see there are number of rivets are 4. So the net area, that is B minus ND into T. So we are having 4 rivets over here. So 300 minus 4 into 19.5 into thickness of the plate. So we are getting the area 1776 square. So the strength of the member is 1776 into 150. That is, we are getting here 266.4 kilonewton. Now, as you have seen, in case of zigzag riveting, the section can fail along the 1 2 3 4, that is this 1 2 3 4, then 1 2 5 6 7, this 1 2 5 6 7, this plane. I will take laser instead so that it will be more. So 1 2 5 6 and 7, earlier was 1 2 3 4. The next is 1 2 5 3 4, this 1 2 5 3 4, this way, and last is 1 2 5 8 9 10. So this is 1 2 5 8 9 10. So this way it can fail. So we are having the particularly, so for the section 1 2 3 4, that is net area, which is straight, so we are cutting it into this, two rivets are there, so cutting it cuts by, or it reduction in area is by two rivet holes. So 300 minus 2 into 19.5 into 8, that becomes 2088 mm square. So this is for the section 1, 2, 3, 4. 1, 2, 3, 4. Now moving towards next section, that is 1, 2, 5, 6, 7. So 1, 2, 5, 6, 7. We'll draw the section over here. So the 1, 2, 5, 6 and 7. So this is the section. Now what will happen? So here S1 equals to S2 and G1 equals to G2. So here S1 equals to this 75 and G is 65. So here this distance is 75 and this is 65. So here S1 and S2 both are the same, and G1 and G2 also same. So while calculating, so we are taking, so net area equals to B minus ND plus S square divided by 4G1, or S1 square divided by 4G1 into T. So 300, that is B. The 3 into 19.5. Why we are taking 3? So we are having these 3 holes over here, 1, 2, and this is the third hole. So 3 into 19.5 plus, only we are having the one diagonal section. That's why here only we are having this one diagonal section. That's why we are adding the into T. So 300 minus 3 into 19.5 plus 1, that is one diagonal section, into 75 square divided by 4 into 65 into 8. So you are getting 2105.08 mm square. So this is all about the section 1, 2, 5, 6, 7. Now moving towards the next section, 1, 2, 5, 3, 4. Where is this 1, 2, 5, 3, 4? Let me erase this. 1, 2, 5. This 1, 2, 5, 3 and 4. So here we are having two diagonal sections. Remember, two diagonal section and three rivet holes. So net area. So B minus ND. So S square divided by 4G, and again S square divided by 4G into D. So 300, that is B, minus 3 rivet holes, that is uh, at 2, 5 and 3, plus 2, that is two diagonal sections, that is 2 and 5, 2 to 5 and 5 to 3. 2 into 75 square divided by 4 into 65 into 8. So that area becomes this much, that is 2278.15 mm square. So this is about section 1, 2, 5, 3, 4. Now moving towards the next section, that is 1, 2, 5, 8, 9, 10. Let me clear this. So starting from here, 1, 2, 5, 8, 9 and 10. So we are having 1, 2, 3, 4 rivet holes, and diagonal sections are 1, 2, 3. Now the net area. So B minus ND plus 3 into S square divided by 4G into D. So 300 minus 4 into 19.5 plus 3 into 75 square divided by 4 into 65 into 8. So that becomes 2275 mm square. So in all the section where we are getting the minimum area, we are having these all sections, that is starting from here we are getting 2088, we are getting 2105, we are getting here 2228, and lastly 2275. So amongst this we are getting the minimum area at this section 1, 2, 3, 4. So therefore strength of the member is the area of that cross section, the minimum area of all these, that is area of cross section, that is 288 into 0.6 into 250. So that becomes 313.2. So same way we are getting the strength of that particular member at that joint. Now the tension splice. So the splices in the tension member are used to join two sections when a joint is to be provided. That is, these replace the member at the joint where it is cut. So why these splices are necessary? Actually, in the market we don't have the longer section or the longer sections as per our requirement. So sometimes we need to cut the particular member, and because of which we need to connect two members. So because the length is not sufficient sometimes, so we need to connect the two members. So that's why this splicing is necessary or needed. So where splices occur in an angle, channel, T or joint section, the force is abstracted from the section through the connection on one side of the joint and is transferred to the or cover plate splice cover plate or angle section. The force is then carried through these covers across the joint and then transfer to the other portion of the section through the connection. The splice section as well as the rivets are designed for the tensile load to be transmitted by the main tension member. There is always a question whether the splice should be designed for the maximum calculated force or the actual strength of the member. So as per IS specification, the splice covers and its connection should be designed to develop the net tensile strength of the main member. So in design of splice plate, there will be a design of tension member of the, or we have to provide the same member and the connection to carry the load which is the main member is carrying. So the problem we are having now. So design a splice for a tension member, sections 160 by 10 mm and 250 by 14 mm. The member is subjected to pull of 200 kilonewton. Assume Fy equals to 250 Newton per mm square. So a splice plate will be provided on both sides of the tension member. Suitable arrangements of the connections design is assumed, and then the width and thickness of the splice plate is computed. Let phi is 18 mm. So the cross diameter is 19.5 mm. So the net tensile strength of the member, assuming the section to be weakened by one rivet hole. So here you can see this is the main plate, that is 250 by 14 mm, and this is the splice plate of 160 by 8 mm. So we need to provide a packing, because here you can see if I draw the cross section, so this is of 14 mm and another plate is of 10 mm. So this thing is 10 mm. So you have to provide a packing, and the plate should be somewhat like this. This is one plate and this is another plate, because we are providing on the both sides. So here packing should be needed. We need a packing that is of 4 mm. It should be of 4 mm. So this is the whole idea behind this splice. Now moving further, so the uh, we are considering the smaller plate, so we are taking width as a 160 minus 1 rivet hole into the this thickness into the strength sigma 80, that is axial tensile strength. So that becomes 210.75 kilonewton. So let us assume the rivets to be power driven. So the values of tau vf is 100 Newton per mm square and sigma pf, that is bearing, that is 300 Newton per mm square. So the strength of the rivet in double shear, because we are having here the two plates, so obviously that becomes a double shear. So 2 into pi by 4 into d square into tau vf. So 2 into pi by 4 into 19.5 square into 100, that is 59.7, and the bearing strength is d into t into sigma pf. So that is 19.5 into 10 into 300, so that becomes 58.5 kilonewton. So the less of these two, that is this, so we are having the rivet value 58.5 kilonewton. So the number of rivets required on each side, so we are having the force 210.75 divided by the rivet value, so we are getting 3.58, but we are providing the 5 rivets. So providing 8 mm 5 rivets on each side. So the two section also is of different thickness, as I told you earlier. So we have to provide the packing. So the thickness of packing, that is 14 minus 10, that is 4 mm. So packing less than 6 mm. There is a clause in IS code. If the packing is more than 6 mm, we need to provide the extra rivet. So here the packing is less than 6 mm, so no extra rivet is required. So this clause is there, in which it has been written the number of rivets or bolts carrying the calculated shear through the packing shall be increased above the number required by the normal calculation by 2.5% for each 2 mm thickness of the packing, except that the packing having a thickness of 6 mm or less, no increase in need to be made. So this is the particularly clause for the extra rivets for packing. Now the width of the plate, that is splice plate. So width of the main tie plate, that is 160 mm. The section for the splice plate is critical of the section XX. So if T is the thickness of the splice plate required, then B minus 2D into 2T into sigma 80, that is net tensile strength of the section. So here we have this B is 160, 2 into 19.5 into 2T into 150, so 210, which is the net tensile strength of the section, into this 10 raised to 3. So we are getting here T by that 5.8 mm, we are providing it 8 mm. So the sum of the thickness of the splice plate should not be less than the maximum thickness of the plates to be connected. So therefore 8 mm thickness should be sufficient, and providing two 160 by 8 mm thickness thick splice plate. So we are here providing the 160 by 8 mm splice plates. So the length of the splice plate. So we are providing the here 5 rivets on each side. So the pitch will decide the particular length of the plate. So minimum pitch, that is 2.5 into 5, so 2.5 into 18 mm, that is 45 mm minimum pitch is there. So provide rivet of the pitch of 60 mm for 80 mm 5 rivets, the edge distance is 29 mm, so providing edge distance of 30 mm. So the length of splice plate, that is 4 into 60, which is, so we are having here this rivet line, then this rivet line, this rivet line, and again this one, and this one. So let me clear this thing. So this is one pitch, this is second pitch, this one is the third pitch, and this is the 4. So pitch distances are 1, 2, this is 3, and this is the 4. So 4 into the 60 we are providing. Now the edge distances. So this is one edge distance that is in between these two. This is first edge distance. Here this plate is here. So here another edge distance is there. The second, same way in these two there is another edge distance. This is third, and here at last we are having this fourth edge distances, which is we are providing, that is 30 mm. So that's why we are taking or making like this 4 into 60, that is 4 pitches, and 4 into 30, that is 4 edge distances. So that becomes a 360 mm. So we are providing two plates of size 360 into 160 by 8 mm. So this is the design of splice. So that is all for today's lecture. So for today's lecture, the references are again the book of S.K. Duggal, that is Design of Steel Structure, then IS code, that is 800 1984, and IS handbook and steel table. So this is for today's lecture. Hence, I would like to declare that your tension member is over. Thank you. Further, we will see the compression members.